Okay, so ladies and gentlemen, welcome. In today's video, we are going to look at the concept of kinetic theory of gases. And don't forget that we have different state of matter. We have solid, liquid, and gas. So the kinetic theory is actually a theory that trying to explain the behavior of particles that are present in all the state of matter. But specifically here, we are going to look at the kinetic theory of gases. And generally, the kinetic energy in solid particles and liquids, it is very small compared to that of the gas. Because in gaseous molecules, the force of attractions of the particles is very less, and that is why they experience high kinetic energy. In fact, they are far apart. They even collide with one another and also collide with the wall of the container because they use direction. So they move randomly, and that's why here we are going to look at the behavior of these gaseous. Let's see, this is the container where you have gaseous molecules. Where you have gaseous molecules. So let's say this is our y-axis and this is our x-axis and this is our z-axis. So assuming now you have the gaseous molecules and these gaseous molecules, of course, each and every one of these gaseous molecules, they have their own mass and velocity. So let's say this is the particles, and it has its own mass and also it has its own velocity. And in this case, we use u as the velocity. So you see, if these gaseous molecules move toward the direction y here, so it means that it's going to cover a momentum plus from point x to point y. So therefore, we are now going to have mass times velocity, which is momentum. And then very importantly, these gaseous molecules at the same time it can also rebound back because the collision is perfectly elastic, meaning that after these gaseous molecules collide with one another, so their collision is perfectly elastic. So as they collide with the wall of the container, they will actually rebound back from point y to point x. And of course, as it is rebounding back, the momentum will be negative at that point. So it's going to be mux. Of course, here is x because it is moving toward the direction of x. So therefore, to get the change in momentum, of course is represented as p, so it's mass times velocity. So because the velocity here we are using delta u. Why are we using delta u not v? Is because we are coming to a point where we have volume. So in order to differentiate them, that is why we are using u for velocity and v for volume. So therefore, as these particles move from x to y, it covers a distance. And as it is moving from points y to x, it also covers another distance. So therefore, n, this L and L, we are going to add them, and this will give us 2L. And of course, to get the change in momentum, we are now going to have mux minus home bracket, minus mux. Then we close the bracket. Now we now have the change in momentum is equal to minus times minus, and this will give us plus. So we now have 2 mux. So we now have 2 mux. Very important to do. And then the next thing after this is that, so now the time it hovers, for example, as it moves from this direction, we can gauge the rate of change of momentum, which is over here. And how do we get that? It's simple. You know that when we say the rate of change of momentum, because this is a changing momentum, so you can get the rates of change of momentum. And when we say the rate of change of momentum, it means over time. So we're now going to have 2 mus, which is very important. But how? It's simple. The time, when we say the rate of change of momentum, it means divided by time. Divided by time. And of course, remember from our basic knowledge in physics, velocity u is something as distance divided by time. But the distance covered by this one is 2L. So therefore, we are now going to have ux when u is equal to 2L divided by t. So now we are now going to make the t subset of the formula. So to make t subset of the formula, this will give us 1 over t. Or to make 1 over t subset of the formula, this will give us 2L divided by u. So therefore, we are now going to make we are now going to substitute. We are now going to substitute this t with 2L divided by u. So therefore, the rates of change of momentum, and of course, I think it is simple from here, because we know that the rate of change of momentum, according to Newton's law of motion, it said that the rate of change of momentum is directly proportional to the force applied. So therefore, the rate of change of momentum is the same thing as force. So therefore, we can now say, therefore, x, that is force in x direction, is now going to be. So we now take this 2 mus, and then we now substitute this t with divided by 2L divided by u. So now, of course, let's make it ux because the force applied is toward x direction. So it's simple. Now, we can actually rearrange this by saying fx is now going to be, of course, we have 2 mus. Already it doesn't have anything here, so you can say divided by 1. And then we have 2L divided by us. So therefore, this one will now multiply this, and then this one will now multiply this. So therefore, f of x is now going to be 2mus is going to be square divided by this time. This is going to be 2L, and this one will now cancel this. So therefore, we are now going to have f of x is equal to mus squared divided by L. And importantly, ladies and gentlemen, we now have mus squared divided by L. So what next? So now we knew that pressure is equal to force times area. So we can now make absolute of the formula by saying F is equal to pressure times area. So therefore now we can now substitute f of x. So we now have PA is equal to mux squared divided by L. And of course, we can make the phi subset of the formula. So make phi subset of the formula, we now have P is equal to mux squared divided by AL. And of course, don't forget that AL is something as volume. That is area times length is the same thing as volume. So here we now have mux squared divided by volume. But very importantly, we should know that from this diagram, we can see that the particles can move in any of this direction. It can move in x direction, it can move in direction, and it can move in z direction. So therefore, this u of x, we can equate them. So u of x squared can be something as u of y squared. And it can also be the same as u of z squared. And of course, when we sum all this together, that is u of x square plus u of y square plus u of z square is now going to give us u square. So now, since we now equate them, so it means that ux is the same thing as uy, so ux plus ux is now going to give us u square. So it means that since ux and uy and uz are all the same, so we can equate them. So we now add this time, this plus this is going to give us 3ux squared is now equals to u squared. So we can now make the ux squared subject of the formula. So let me continue here. After doing this, it is now going to give us ux square. Yeah, we have 3 that is equal to u square. So we can now say divide both sides by 3 by 3. So this will now take care of this. So we now have ux square is equal to u square over 3. And this will now give us, from here, we can now have our pressure. Our pressure is now equals to, very simple, it was, is now going to be mu, because our u here is no longer ux, is u square divided by 3v, because the u here, the ux square become ux square divided by 3. And that's why we have mu square divided by 3v. So ladies and gentlemen, it depends on the number of molecules that are present inside the container. So that is why sometimes this can be expressed as E is equal to nm ux square divided by 3v. So from here, this is actually the derivation of the equation. So you can obtain a lot of things from here. You can obtain a lot of polar equations from here. You can get Boyle's law, you can get Charles law, you can get general gas law, and you can get a lot of things from here. So this then indicates that the number of molecules that are present in the container. Like for example, from here we can derive what we call a root mean square piece. And let's see how we can go about it. So here, let's make this use of that of the formula. So we can make use of that of the formula. So we can multiply this and this can give us 3pv is equal to nmu square. But it depends. Let's say you have only one molecule inside the container. So for one molecule, we can decide to remove this here, and this will give us 3pv all over m is equal to u square. And of course, you can make this u subject of the formula, so this will now take care of this. So this u is equal to 3pv all over m is called root mean square speed. It's called root mean square speed. And very importantly, from here, from the general gas equation, we know that we have general gas equation, Pv is equal to Nt. So you can actually substitute Pv with Nrt in this equation. You can do that. And after we do that, so we now have Pv, so you can substitute it by saying U, which is root mean square speed. This one we call the root mean square speed is equal to square root of Nrt, 3nRT all over M. And this is also root mean square speed, while N here stands for mole. So this is actually root mean square speed. So from here you can write a lot of equations. So ladies and gentlemen, without wasting much of my time, I think we are going to look at some of the examples that are associated with this. But some of you will now say, are we going to have this kind of questions in objectives? Of course, it's possible. They can ask you what will be the equation, what this equation would be at the rate of change of momentum. So you know how to express it. The root mean square speed, you can play around it and get all these things. So ladies and gentlemen, thank you. So I am going to do another video for some part of the calculation. Thank you. See you next.